Hello, ma'am.
Good evening, sir. Sir, you can start, sir.
Good evening, all. Good evening to all of you.
Good evening, sir.
So yesterday we were learning few concepts. That is, we learned few quiet concepts yesterday. That is, we learned lowering of vapor pressure. We learned Raoult's law. We learned, and the limitations of Raoult's law. We learned. We solved few of the problems. We will solve some of the questions based on Raoult's law today, and also we learned a difference between ideal solution, non-ideal solution, and we learned non-ideal solutions of two types: solution showing positive deviation and solution showing negative deviation. And we learned the graphical representation of solution showing positive deviation and also negative deviation. And we did few of the questions yesterday based on this azeotropic mixture or non-ideal, ideal solution showing non-ideal solution showing positive deviation or negative deviation. And we learned also something called as azeotropic mixture, constant boiling mixture. Some examples we learned yesterday. Now we'll have to continue with the few questions based on lowering of vapor pressure or the concept of vapor pressure. Little longer questions which will be asked in the competitive exams. The time allotted will be minimum, so you need to practice. Now, the first question what we're going to learn is an aqueous solution of glucose is made by dissolving 10 grams of glucose in 90 grams of water at 303 Kelvin. If the vapor pressure of pure water at 303 Kelvin is 32.8 millimeters of mercury, what would be the vapor pressure of its solution? What would be the vapor pressure solution? What is given now? One of the given is what they've given is they've given you the vapor pressure of pure water. Now, when we say vapor pressure of pure water or pure component, we represent it as P naught. We'll mark solvent. Water is a solvent, therefore, as A. So vapor pressure of a pure water they've given as 32.8 millimeters of mercury. So one of the way to express pressure is in terms of what millimeters of mercury. What else is they've given? They've given you the mass of glucose. Mass of glucose they've given you. The mass of glucose they've given you is 10 grams of glucose. And they've given you mass of water also. Mass of water. What is the mass of water they've given? They've given 90 grams. So 10 grams of glucose is dissolved in 90 grams of water. So this is what they've given. So we know from Raoult's law, or maybe we can write like this, according to Raoult's law. According to Raoult's law, we know that the vapor pressure of the solution, is given as PA will be equal to P naught A into mole fraction of the solution, or the mole fraction of the solvent, where P naught A is nothing but the vapor pressure of pure water. XA is the mole fraction of, what is XA? It is the mole fraction of water. It's the mole fraction of water. Now, how do we calculate the number of moles of water? Now, they've given you mass of water to be 90. What is the number of moles of water? Number of moles of water will be equal to, what is the weight of water they have given? 90 grams divided by the molecular mass of water is 18. Therefore, it's 5 moles. So how do you find the number of moles? Weight in grams divided by molecular mass will give you the number of moles. So number of moles of water is 5 moles. So similarly, what will be the number of moles of glucose? Number of moles of glucose Weight of glucose, they've given 10. Molecular formula of glucose is C6H12O6. So the molecular weight of glucose is 180. You should remember this. Molecular weight of glucose is 180. So 10 divided by 180, it will give you 0.0556 moles. So we calculated the number of moles of water as well as we calculated the number of moles of glucose. So what is the mole fraction of water now? The next is, because we want XA. XA is nothing but mole fraction of water. How do you calculate the mole fraction of water now? Mole fraction of water, XA will be number of moles of water. How much is the number of moles of water? 5 divided by what is the total number of moles? Total number of moles is water 5 moles plus the glucose number of moles is 0.0556. So on simplification, it will be mole fraction will be 0.989. Mole fraction of water is 0.989. Therefore, what is the vapor pressure of the solution now? Vapor pressure of the solution is 32.8 millimeters of mercury into mole fraction of water. We just calculated as 0.989. On simplification, we will get this to be 32.44 millimeters of mercury. See, vapor pressure of water, pure water is 32.8. Vapor pressure of its solution decreases. We always learned P naught is greater than P. Vapor pressure of a pure component will be greater than the vapor pressure of a solution. See, this is vapor pressure of water, 32.8. But when you add 10 grams of glucose, the vapor pressure decreases to 32.44 millimeters of mercury. Hence, the answer for this question is option A, 32.44 millimeters of mercury. Any clarification with this? It's a lengthy problem. These kind of problems only will be asked in the competitive exam. You should be fast to work out this problem. There's a simple formula. So this formula, if you remember, and if you're able to calculate the number of moles, and then becomes easy. Did you follow this?
Yes, sir.
Yes. The next question. At 298 Kelvin, the vapor pressure of benzene is 2, and it's wrongly typed. I typed it wrong. The vapor pressure of benzene is 0.256, 0.256 bar. So bar is also a representation to the unit for pressure, right? A way of expressing the pressure, 0.256 bar. And the vapor pressure of toluene is 0.0925 bar. If the mole fraction of benzene is 0.40, if the mole fraction of benzene is 0.40, what is the total vapor pressure of the solution? They're asking what is the total vapor pressure of the solution. So according to Raoult's law, we can understand the vapor pressure of a component is equal to vapor pressure of the pure component or vapor pressure of a pure liquid into mole fraction of the component. Mole fraction of the component. That is nothing but P is equal to P naught A into XA. So they've given what they've given. They've given mole fraction of benzene. They've given mole fraction of benzene to be 0.40. The question they've given, mole fraction of benzene is 0.40. Now, vapor pressure of pure benzene. Vapor pressure of pure benzene also they've given. What is the vapor pressure of pure benzene they've given? That is P naught of benzene. P naught of benzene they've given to be 0.256 bar. So therefore, we can write, this is a lengthy problem. See, these are all given. So therefore, we can write the partial vapor pressure of benzene. What's the partial vapor pressure of benzene? Partial vapor pressure of benzene will be given as vapor pressure of pure benzene into mole fraction of benzene. So vapor pressure of pure benzene is 0.256. What is the mole fraction of benzene? In the question they've given us 0.40. So multiply this by 0.40. So you will get 0.1024 bar. 0.1024 bar. This is the vapor pressure of pure benzene. This is the vapor pressure, not pure benzene, vapor pressure of the solution, benzene. Now just observe. Now, yesterday we learned the three graphs, if you remember. So here, the mole fraction on the extreme left is 1. As we go across, the mole fraction becomes 0. Here, the mole fraction in the extreme is 0. And as we go on the right side, the mole fraction becomes 1. Now, what is that you're supposed to remember is XA plus XB will be always equal to 1. At any instant in time, the mole fraction of the solute and mole fraction of the solvent will be equal to 1. If that is the case, now we solved the mole for benzene we learned the partial pressure of benzene to be what? 1024 bar. If that's the case, what is the mole fraction of toluene? The mole fraction of toluene, the next component is toluene. The mole fraction of toluene, X toluene, will be equal to 1 minus 0.40. That will be equal to 0.60. Just now I gave you the explanation. Sum of the mole fraction of the solute and solvent will be always equal to what? 1. So mole fraction of benzene, they've given us 0.40. So what will be the mole fraction of toluene? It will be 1 minus 0.40. That's nothing but 0.6. So they also have given vapor pressure of toluene. They were given the vapor pressure of toluene to be what? 0.0925 bar. Therefore, what will be the pressure of toluene? Pressure of toluene will be 0.0925 into 0.60. That will be equal to 0.055 bar. So this is the contribution of what? The pressure toluene. So they're asking you, what is the total vapor pressure? Total vapor pressure will be sum of the vapor pressure of benzene and sum of the vapor pressure of what? The toluene. So the total vapor pressure, maybe I can write here, the total vapor pressure is equal to vapor pressure exerted by benzene plus vapor pressure exerted by toluene. So vapor pressure exerted by benzene is 0.1024 and the toluene is 0.055. So on addition of these two, we will get 0.158 bar. The answer, what you'll get is 0.158 bar. Did you understand this? Did you understand this? Did you follow this?
Yes, sir. Yes, sir.
Yeah. See, these are lengthy problems. You should know some of the formulas which has been taught in the class. So you should practice the formula so that it will be easy for you to answer. The next question, the vapor pressure of chloroform and dichloromethane at 298 Kelvin is 200 millimeters of mercury and 415 millimeters of mercury respectively. The mole fraction of each component, they're asking you to calculate the mole fraction of each component. It's a simple problem. Now, one is chloroform. What's the formula of chloroform? CHCl3. The molecular weight of chloroform is 119.5. You know how to calculate. Carbon is 12, hydrogen is 1, chlorine is 35.5 into 3. So it will give you 119.5. So dichloromethane is CCl2 and H2 or CH2Cl2. We can write it as CH2Cl2. So the molecular weight of dichloromethane, if you calculate, it will be 85 gram per mole. So they have given vapor pressure of chloroform and dichloromethane. They've given the vapor pressure, pure component. Now, how do you calculate this? Now, firstly, you need to calculate the mole fraction. Now, in order to calculate the mole fraction, we need to know the weight of the component. I mistyped here. Maybe we can write 25.5 grams of chloroform and 40 grams of dichloromethane. I didn't type here. So 25.5 grams of chloroform and 40 grams of dichloromethane. So what will be the number of moles of chloroform? The first thing what you're supposed to do is to calculate the number of moles. Number of moles of chloroform is, they've given 25.5 and the molecular mass of chloroform we calculated is 119.5. That will be equal to 0.213 mole. Similarly, number of moles of dichloromethane, CH2Cl2, That will be equal to, what is that they've given? They've given 40, and the molecular mass we calculated to be what? 85. So that will be equal to 0.470 mole. 0.7470 mole. So what will be the total number of moles now? The total number of moles will be total number of moles. Total number of moles will be equal to 0.213 plus 0.470. That will be equal to 0.683. This is the total number of moles. The question is, they're asking the mole fraction of each component. Now, in order to calculate the mole fraction of each component, now what will be the mole fraction of chloroform? Mole fraction of chloroform will be number of moles of chloroform, that is 0.213, divided by total number of moles, that is 0.683. So this gives you 0.312. Similarly, the mole fraction of dichloromethane, CH2, Cl2. What's the number of moles of CH2, dichloromethane? We calculate it to be 0.470. Total number of moles is 0.683. Now, on simplification, we will get this to be dichloromethane, so it will be 0.688. So therefore, the answer for this question is option A, 0.312 and 0.688. I hope you followed this problem also. They're asking you to calculate the number of moles. So mole fraction of each of the component. So this was typed. This was not typed. So please remember, this was not typed. So this was given. This is given in the question. This is given in the question. Please pay attention for this. Can we continue or any clarification with this problem?
No.
No? Yeah. In the next problem, 1 mole of heptane. Vapor pressure of heptane is 92 millimeters of mercury, and 4 moles of octane. The vapor pressure of octane is 31 millimeters of mercury. Forms an ideal solution. Find out the vapor pressure of the solution. What is the vapor pressure of the solution? Now, they've given 1 mole of heptane and 4 moles of octane. Forms an ideal solution. And they've given the vapor pressure also. What is the vapor pressure of the solution? The vapor pressure of the solution will be what? The sum of P naught of A into XA plus P naught of B into XB. So this is the total vapor pressure, sum of the vapor pressure. So total vapor pressure, if you remember, it's an ideal solution, they say. For ideal solution, how the graph was, if you remember the graph, we drew like this. And we learned it to be like this. And PS is equal to P naught of A and P naught of B. This is what we learned. PA into PB we learned. So PA is what? P naught of A into XA. PB is what? P naught of B into XB. So now what is P naught? They've given P naught of A 92 and P naught of B they've given to be 31. But what is XA and XB? They've not given. We'll calculate XA and XB. Now they've given number of moles of heptane. Number of moles of heptane they've given to be 1 and number of moles of octane they have given to be 4. So what will be the total number of moles? Total number of moles will be equal to 5. Total number of moles is equal to 5. Now what is P naught A? They have given 92 into what is the mole fraction of A? Number of moles of A is 1 divided by total number of moles we found out to be what? 5, 1 by 5. In plus of P naught of B they have given to be 31. And what is XB? XB is number of moles of X is what? XB is what? 4. 4 divided by 5. On simplification, you will get this answer to be 43.2 millimeters of mercury, mmHg. So the answer for this question is also option A. It is very simple. We need not have to calculate the number of moles because the question itself they've given 1 mole and 4 moles. So total number of moles is what? 1 plus 4, that's 5. So you can calculate the mole fraction of XA is 1 by 5 and mole fraction of XB is 4 by 5. Multiply by the total, the pure vapor pressure, then we will get the answer to be 43.2. Clear with this problem?
Yes.
Yeah.
Yes, sir.
Next problem. The vapor pressure of benzene at 90 degrees Celsius is 1020 torr. Torr is also one more method of expressing the pressure. We learned millimeters of mercury, we learned bar, and there's a third way to express the pressures in terms of torr. A solution of 5 grams of solute in 58.5 grams of benzene has vapor pressure 990 torr. The molecular weight of the solute is. The molecular weight of the solute is. In order to find this relative lowering of vapor pressure definition, I have to derive something. I will derive here only, then I'll erase this and work on the problem. Now, relative lowering of vapor pressure is given by the relation P naught minus P divided by P naught is equal to N2 divided by N1 plus N2. Now, 2 stands for solute, 1 stands for solvent. What is this relative lowering of vapor pressure? It says, what is Raoult's law? One more way of representing or defining Raoult's law. Raoult's law can be defined as the relative lowering of vapor pressure is equal to mole fraction of the solute. Now, when we say relative lowering of vapor pressure is equal to mole fraction of the solute, this derivation is there in your 12th. Please pay attention. P naught minus P divided by P naught is equal to, I can write N2 divided by N1. Why I write only N2 by N1? I ignore N2 because N2 is very, very less compared to N1 because we're preparing a dilute solution. In dilute solution, number of moles of solute will be very, very less. Therefore, N2 is neglected compared to what? N1. Therefore, the formula reduces to P naught minus P divided by P naught is equal to N2 by N1. So, if I write P naught minus P divided by P naught is equal to N2 can be written as W2 by M2 and N1 can be written as W1 by M1 because weight in grams divided by molecular mass gives us number of moles. So N2 is written as what? W2 by M2 and N1 is written as W1 by M1. So on simplification, we can write P naught minus P divided by P naught is equal to W2 into M1 divided by M2 into W1. This is the formula. So remember this formula. This is the formula wherein we can find the molecular weight of the solute. So the molecular weight of the solute is M2. What will be M2? We can write M2 as W2 M1 by W1 into P naught divided by P naught minus P. Can we write this formula to calculate the molecular mass of the solute? This derivation, did you understand? It's a simple derivation. Did you follow this derivation?
Yes, sir.
Yeah. Now tell me what is molecular mass M2 now. M2 will be what? W2. What is the W2 they've given? 5 grams. They've given 5 grams solute. And M1. M1 is what? So they have given vapor pressure of benzene at 90 degrees. This is a solution of 5 grams of solute in 58.5 grams of benzene. So M1 stands for molecular mass of the solvent. Here the solvent is benzene. The molecular mass of solvent is 78. Benzene is C6H6. The molecular mass of the solvent is 78. Don't get confused. M1 stands for molecular mass of the solvent. W1 stands for the weight of the solvent. M2 stands for the weight of molecular mass of solute. W2 stands for weight of solute. So this is C. 2 stands for solute. I will write here. M1, M2, W1, it corresponds to solvent, and M2, W2 corresponds to solute. Molecular mass and weight. So 78 is the molecular mass of the solvent divided by W1. What is the weight of the solvent? It is 58.5. 58.5 into what is P naught? They have given vapor pressure of a pure benzene as 1020 divided by what is P naught minus P? 1020 minus 990. This is nothing but the vapor pressure of the solution. So on simplification, you get this M2 as 220. Is it right? The answer for this question will be option A. Did you understand how to work out this problem? See, this formula you are supposed to remember. And what does M1, M2 stands for? You should remember. M1 stands for the solvent, M2 stands for solute. I've written it there. So when you're reading, referring to this video, you will understand better. So did you understand this derivation as well as the problem?
Yes, sir.
Yes.
Yes, sir.
Yeah. So the next problem is based on this question only. We will not based on this question, based on this formula. This next question we will learn. Now the next question for our discussion is: an aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molar mass of the solute? What's the molar mass of the solute? Now, what is given? They have given vapor pressure of pure water. You should remember. What is that vapor pressure of pure water? Vapor pressure of pure water is 1 atmosphere pressure. That 1 atmosphere is 1.013 bar. So atmosphere is also one of the unit to express the pressure. So P naught of water, pure water, is 1 atmosphere, or it's 1.013 bar. Now, what is the vapor pressure of the solution they've given? Vapor pressure of solution, they've given PS, or we can write only P, they've given to be 1.004. They've given the pressure of the solution to be 1.004 bar. What is the mass of the solute? Mass of the solute, what they've given? Mass of the solute, normally we represent as W2. They have given mass of the solute, 2% of non-volatile solute. What do you mean by 2% of non-volatile solute? 2 grams and 100 grams the solvent. So that will be giving you 2%. So they have not given you the weight of solute directly. They have given it to be 2% solution. 2% solution means it is 2 grams. What is the mass of the solution? The mass of the solution is 100 grams. So mass of the solution, since we're talking about percentage, it will be for 100. Therefore, it will be mass of the solution will be 100. Now tell me, what will be the mass of the solvent? What will be the mass of the solvent? It will be 100 minus 2. That will be 98 grams. Mass of the solute, they've given us 2 grams. Mass of the solution, 100 grams. We take it. Why we take it as 100 grams? Because it is in percentage. Therefore, we take it as what? 100%, 100 grams. And what's the mass of the solvent? 98. Now, they're asking you to find the molecular mass of solute. So how do you find the molecular mass of solute? Now, in order to find the molecular mass of solute, the formula in the previous question we learned. What is the molecular mass of the solute? We learned it as M2. The formula I'll write here. M2 will be equal to W2M1 divided by W1 into P naught divided by P naught minus P. So what is W2? What is the weight of the solute they were given? Weight of the solute is 2. What is M1? Molecular mass of the solute. We have molecular mass of the solvent. See, they say they have not mentioned the solvent anywhere. It means you have to consider it to be water. When we consider it to be water, the molecular mass of water is 80. What is the weight of the solvent? The weight of the solvent is 98. Into what is P naught? P naught is 1.013. And what is P? P is 1.013 minus 1.004. So this is in brackets we will write so that it's one term. So on simplification, we will get the answer to be 4,135 grams per mole. Or we can write the molecular mass of the solute, or molar mass of the solute is 41.35 grams per mole. You know more compound has molecular mass 4,135. So it's written as 41.35 gram per mole. Hence the answer for this question is option A, 41.35. The next question. Did you understand this? Did you follow? This is a simple problem as we did the earliest one. Direct substitution. Did you follow?
Yes, sir.
Yeah. The next question. Vapor pressure of pure water at 298 Kelvin. Sorry. 298 Kelvin is 23.8 millimeters of mercury. 50 grams of urea is dissolved in 850 grams of water. Calculate the vapor pressure of water for this solution and its relative lowering pressure. So they're asking you to calculate the vapor pressure of water, and they're asking you to calculate the relative lowering of vapor pressure. Now, what is given? They've given vapor pressure of pure water. Now, pure water vapor pressure, they represent as P naught, that is 23.8. They've given you mass of the solute. Urea is the solute. Mass of the solute, that is W2, they've given to be 50 grams. Is dissolved in 850 grams of water. What is the mass of solvent they've given? Water is the solvent. So W1, they've given 850 grams. They're asking you to calculate the vapor pressure of the solution, as well as they're asking you to calculate the relative lowering. So now tell me, what is M2? Molar mass of water. We know the solvent is water. So molar mass of water, it is capital M1, that is 18 grams. And also, you should know what is the molar mass of urea. Molar mass of urea. Urea, they've mentioned it as urea. So molar mass of urea, we write it as M2. What is molar mass of urea? Urea formula is NH2CONH2. So the molecular weight of urea is 60. You should remember the molecular weight of urea is to be 60. Now we need to calculate. Firstly, we can calculate P naught minus P divided by P naught is equal to N2 by N1, or we can write P naught minus P divided by P naught is equal to W2 by M2 divided by W1 by M1. This is nothing but relative lowering of vapor pressure. So what is W2? We found out W2 in the question. They've given W2 to be 550 grams of urea, and a molecular mass of urea we found out to be 60, divided by W1 is 50. Water, weight of water is 850, divided by molecular mass of water, everybody knows it is 18. So on simplification, you will get 0.017. So relative lowering of vapor pressure is 0.017. Now the next part is, they are asking you to calculate what is the vapor pressure of the solution. In order to calculate the vapor pressure of the solution, can I write P naught minus P divided by P naught is equal to 0.017. Just now we calculated this. Relative lowering of vapor pressure is 0.017. Since we want P, we have to find the vapor pressure of its solution. Now what is P naught? They've given P naught to be 23.8. So on substitution, 23.8 minus P divided by 23.8, that will be equal to 0.017. So on simplification for P, you get the answer to be 23.4 millimeters of mercury. It is a simple mathematics, cross multiply and divide. So it will be mercury, Hg, 23.4. Hence the answer for this question is option A, 23.4 millimeters of mercury and 0.017. 0.017 is the relative lowering of vapor pressure. Is it clear with this problem?
Yes, sir.
So relative lowering of vapor pressure is one of the colligative property what we have completed. In relative lowering of vapor pressure, we spoke about Raoult's law. We learned the ideal, non-ideal solution difference. We learned with the non-ideal solution showing positive deviation and negative deviation. We also learned with the azeotropic mixtures, and we worked out a few of the problems on azeotropic mixture and vapor pressure concept. So the next concept what we'll have to learn today is called as osmosis and osmotic pressure. What is this osmosis and osmotic pressure? We will learn what is osmosis and osmotic pressure in a minute time. If you have any clarification, you can ask me till what we have done. If you have any clarification, you can ask. Any problem? If you're not able to answer, you can ask me quickly so that we can continue with the topic. The next colligative property we'll be learning is osmotic pressure. Any clarification?
Yes, sir.
Tell me. Is there any clarification or no? Oh, yes. What does it mean? You tell me. No clarification?
No, sir.
Okay. One minute. All right. So the next property or the next colligative property is osmosis and osmotic pressure. Now, what is this osmosis? We will learn about osmosis a little later. Now you tell me, I take a glass of water, pure water, and into this pure water, assume that we are adding a drop of ink. What will happen? What will happen? When you add a drop of ink, what will happen?
So the ink will spread all over the water.
The ink will spread all over the solute container. Very good. Now we have to understand a term called as diffusion. Diffusion means movement of particles from higher concentration to lower concentration. That's called as diffusion. Now, for an example, at home, don't do this. At home, if you try to open the gas valve, what happens? The gas which is in the cylinder slowly spreads in the room, complete. So in the room, we have what? Atmospheric air is there, but when you open the gas stove, what happens? Without lighting, the gas starts moving and gets accumulated in the whole room. That process is called as diffusion. So movement of particles from higher concentration to lower concentration will be called as diffusion. Now we are not talking about diffusion, we are talking about something called as osmosis. What is this osmosis? We will try to understand what is osmosis. In order to understand osmosis, we need to understand something called a semi-permeable membrane. What is this semi-permeable membrane? Semi-permeable membrane. A membrane which will permit to the flow of only solvent particles is called as semi-permeable membrane. What is a semi-permeable membrane we are using in this osmosis process? A membrane which will allow only the solvent particles to move. Example for semi-permeable membrane, we can give a natural example or which exists is parchment paper bag. Cellulose, it's made of paper bag made of cellulose will be called as parchment paper bag. Animal bladder, any animal bladder is an example for semi-permeable membrane. In specific, they say pig's bladder. I don't know why they call pig's bladder to be a semi-permeable membrane. In general, we write it as what? Animal bladder. And synthetic semi-permeable membrane. You should remember all this. Semi-permeable membrane. SPM stands for semi-permeable membrane. It is potassium ferrocyanide. Copper ferrocyanide, not potassium, copper ferrocyanide. This is an example for synthetic semi-permeable membrane. Copper ferrocyanide. What is the semi-permeable membrane used in the osmosis process? A membrane which will permit only the solvent particles to move, not the solute particles. You know what is solute and solvent. No one need to explain the same thing again. Now, a membrane which allows only the solvent particles to move through is called a semi-permeable membrane. Example, parchment paper bag, animal bladder, cellophane. Cellophane is also an example for a semi-permeable membrane. Synthetic semi-permeable membrane, copper ferrocyanide. Now, we will try to understand what is osmosis. You understood what is diffusion. You understood what is semi-permeable membrane. Examples for semi-permeable membrane you can remember. Hopefully you remember. Right now we will learn to understand what is osmosis. Now, in order to understand the osmosis, we'll take an experimental part and we'll try to understand. This is a graduated tube, and we have a bulb here at the bottom and a semi-permeable membrane attached to the bottom. This is semi-permeable membrane. This is a graduated tube, 1, 2, 3. Maybe we'll mark it as 1, 2, and 3. And this funnel is called as Thistle funnel, THISTLE, Thistle funnel, graduated funnel. And here it's a semi-permeable membrane. Now what we do is, till the mark 1, we will fill a solution. Now assume that I've filled a glucose solution. Now what is this solution? This is glucose solution. Glucose solution. Now this Thistle funnel, which has glucose solution till 1, we place in a beaker containing water. We place in a beaker containing water. Beaker containing water. Water is here. This is water. Now you tell me, this is a concentrated solution because here we have glucose molecules. In water, we do not have glucose molecule. So I can consider water to be dilute and glucose solution to be concentrated. Did you understand what I'm trying to tell? We have a Thistle funnel. In the Thistle funnel, we have filled the glucose up to marking 1, and we have a semi-permeable membrane. We have dipped this Thistle funnel in water, beaker containing water. Leave it for some time. When we leave it for some time, what happens is the water molecules starts getting into the Thistle funnel. Water molecule starts getting this. That means what happens? Here, the volume is increased. Inside the funnel, what happens? The volume increases. When we say inside the funnel, the volume increases, water would have diffused, not diffused, water would flow into what? The Thistle funnel, get into the Thistle funnel. So therefore, from 1, the solution raises maybe to 3. We'll assume that it raises to 3. This process is called as osmosis. This process is called as osmosis. What is osmosis? Movement of solvent particles from the region of lower concentration to the region of higher concentration through a semi-permeable membrane is called as osmosis. What is osmosis? Movement of solvent particles from a region of lower concentration to the region of higher concentration through a semi-permeable membrane is called as osmosis. Now just observe, I told you, water does not contain glucose. We'll assume it to be what dilute. Maybe otherwise, if I want it to be more specific, we will learn like this. Here, this glucose contains 1 molar inside the Thistle funnel. This is a dilute glucose solution. This blue color, what we are talking about, can be taken as a dilute glucose solution. I'll take it as dilute glucose solution. When we say dilute glucose solution, I take 0.1 molar. Here it is 1 molar, here it is 0.1 molar. So now what happens when you keep this in the beaker containing dilute glucose solution, only the water molecules will get into, because water is a solvent. As per the definition of osmosis, osmosis is movement of the solvent particles from a region of lower concentration to a region of higher concentration through what a semi-permeable membrane is called as osmosis. Did you understand what is osmosis, students? You follow what is osmosis?
Yes, sir.
Yes, sir.
Yes. Now we have to learn something called as osmotic pressure. What is this osmotic pressure? This osmotic pressure is represented by letter pi. Osmotic pressure is represented by letter pi. Now we will try to concentrate on the same experiment. Now, when we say we try to concentrate on the same experiment, now we have taken a glucose solution till 1 ml, reading here, and we are immersing. Now, what we are doing is we are fixing a piston here. We are fixing a piston here. This is a piston. This is fixed piston. See, this thistle funnel contains 1 molar glucose solution. It is dipped in a solution containing 0.1 molar, no doubt. Experimental procedure is same. When we defined osmosis, piston was not there. Now we are trying to define osmotic pressure. So I am fixing a piston here. This piston is fixed. It cannot move. You tell me will the water molecule get enter now into the thistle funnel? Will the water molecule enter? Will the solvent particle enter into the thistle funnel now through semi-permeable membrane? Will the water molecule enter the thistle funnel because this piston is fixed? This piston cannot move.
Sir, no, sir.
No. So that means you are applying external pressure so that osmosis will not take place. That external pressure, what you apply in order to prevent the osmosis, is called as osmotic pressure. The external pressure applied in order to prevent the flow of solvent particles from the region of higher concentration to the region of lower concentration through what? Through semi-permeable membrane is called as osmotic pressure, or maybe we can write external pressure applied in order to prevent what? Osmosis is called as osmotic pressure. So osmotic pressure, what do we represent? We represent osmotic pressure by the letter of what? Osmotic pressure applied in order to prevent the flow of solvent particles from the region of higher concentration to the region of lower concentration through a cell is called as osmosis. So osmosis, the flow of solvent particle from pure solvent or from solution of lower concentration into a higher concentration through semi-permeable membrane is called as osmosis. Osmosis can be divided into two: exoosmosis, endoosmosis. We will learn this exoosmosis, endoosmosis, reverse osmosis. Exo and endo we do not have in the syllabus, but we have reverse osmosis we will learn. But what is this exoosmosis? The outward osmotic flow of water from a cell containing an aqueous solution through a semi-permeable membrane is called as exoosmosis. For example, egg, after removing the hard shell, placed in this concentrated sodium chloride solution will shrink. Why the egg, after removing the hard shell, placed in a concentrated NaCl solution will shrink? Because from this egg, water will flow outside. Water will flow outside. Therefore, what happens? The egg shrinks. Now, endoosmosis, the inward flow of water into the cell. Now, you know raisins. So raisins, if you put it in water in the night, and tomorrow morning, the next day morning, if you see, the raisins would have swollen. Why? Water will enter into the raisins. Dry grapes, we call. Raisins is nothing but dry grapes. The inward flow of water into a cell containing an aqueous solution through a semi-permeable membrane is called as endoosmosis. Exoosmosis, from the cell outside. Therefore, what happens? The cell shrinks. Endoosmosis, water flows into the cell. So what happens? The cell swells. That's called as endoosmosis. We will learn reverse osmosis in detail because reverse osmosis is there in the syllabus. This also is there. Exoosmosis and endoosmosis also is there. So when the water or any electrolyte flows out of the cell will shrink. When this water flows into the cell swells. That's called as endoosmosis. Reverse osmosis we will learn with experimental experiment I have to teach you. That we will learn in the next class. Ma'am, I'll stop the class, ma'am. I'll stop because this we need to have.
Yes, sir.
I'll stop the class now. Okay.
Yes, sir. Yes, sir. Thank you, sir.